This video is for section 3.4, numerical descriptive measures of a population. Now we've talked about sample measures, sample mean. Well, the population mean is essentially calculated the same way. We use different notation. Now the population size is denoted by capital N. It just would mean how many items are in your population. And they use a parameter Greek letter called mu. It's kind of a weird looking U with the extra tail there on the left there, so that's a Greek letter. Population parameters are often represented by Greek letters, whereas sample measures are not. Remember, we use X bar, the X with a line above it, to represent sample mean. So here's the formula, which is essentially the same as it was for sample mean, except for notation. They're saying that the population mean mu means the sum of all your x's. The x is just each particular x, like x1, x2, representing each individual number. Add those up and divide by the n, the number of values in a population. So you calculate that pretty much the same way. And so here's an example below. I put 5 numbers down there, and I'm saying that that they're defined to be a population. So you can see that they are calculated exactly the same way. So you just take those 5 numbers, 2, 11, 6, 9, 10, add them up, divide by 5. There you go. So pretty easy, just like it was for sample mean. Okay. All right, so let's scroll on down and see what we got here. Now we have population variance. Now this is going to be a little bit different. One slight difference between this and sample variance. One slight difference, but it changes the answer and makes it a different answer. You may recall, in fact, I could bring that up real quick. Let's see. Didn't think about it. I would already have this file pulled up. Let's see. Probably in 3.2. Yes, when we did the sample variance back in 3.2. But notice this is what I was trying to focus on right here. Then I'll go back to 3.4, is the denominator here. We divided by n minus 1 for sample variance. For population variance, we do not do that. We divide only by the population size n. So you see, that's what's going to make these answers be a little bit different. So the xi minus mu all squared, that's the same thing as doing the xi minus x bar squared. So the calculation, whether it's sample or population, it's just the symbol's different. Here it has x bar for sample mean, but the numerator is exactly the same. So the way you calculate the numerator, so let's say you were calculating the sample variance, and you also wanted to get, and all of a sudden we said, hey, what if this was a population? We wanted to get the population variance. You wouldn't have to start over or anything like that, because once you had that value in the numerator, and we're taking the same numbers and now saying it's a population, we would just divide by n instead of n minus 1. So it'd be real easy to get the other value. And of course, as we've mentioned, standard deviation is always the square root of the variance. So population standard deviation. Oh, I forgot to mention, excuse me here, that's that little O with a little tail at the end of it, that is also a Greek letter. Surprised they didn't mention that, unless I just didn't copy that part out of the book. But that's a sigma. Actually, it's a lowercase sigma. Sigma squared. Variances always have a square with it. In fact, not that you have to know this, but that's a little sigma, and actually the little zigzag thing right there, that is capital sigma. And the little O with the hook's the lower sigma. So the O without the hook, the sigma without the square, means it's standard deviation, which is just the square root of the variance. So here's that shortcut formula I've mentioned before that you can use for the numerator sum of squares. You do it the same way, where you take you square each x and add them up, and you subtract the sum of the x's squared all over n. That's the numerator. Then the whole thing is divided by n. So I just chose to do it that way. You could still do it the other way, where you subtract the mean if you want to. That's up to you. Now we have these 5 numbers, 2, 10, 6, 5, 9. Notice that I have the left column and the right column are squared. And so the sum of the x squareds is this bottom number here, 246, which then the sum of the x's is 32, so that 32 number is squared, and that number is divided by 5 because we have 5 values. Not all that, only the 32 squared is divided by 5. Then the whole thing is divided by 5, and we get 8.24. So that would be the population variance. And the population standard deviation would just be the square root of that number, which is 2.87. All right. Now, if you were using a calculator and you wanted to try to use sort of the same thing with Excel also, Excel, well, the calculator, they don't give population variance. They only give sample variance. But all you have to do is take, here's a little conversion formula I came up with right here. Now you have to take the variance before you square root it. If you take the variance, sample variance, and then multiply it by n minus 1 divided by n, that will give you the population variance. And then you can square root it to get the standard deviation. So let's say if we took a look at, let's see if I've got one. All right, and the same thing. Now, of course, remember in the calculator, we've talked about this before. The TI, you have to, it only gives you the standard deviation, so you have to square it to get the variance. I think I'll do that real quick here in a second. But anyway, I did this in Excel. Same 5 numbers we did. So this answer gives you 10.3 for the sample variance, and we wanted population variance. So what I did is, okay, I had to pause for a moment to correct an error in the notes that were using numbers from a different problem that didn't match what we're doing here. Well, anyway, going back to showing you how to convert from sample to population, this is still true, n minus 1 over n, or you can actually do it with the standard deviations as long as you use the square root of n minus 1 over n, which I could have put that in that box, but I didn't. Yeah, but I can show you that real quick too. Well, anyway, if you take the sample variance that Excel gives you, right there, 10.3, and you can see inside the calculator box, if I multiply it by n minus 1 over n, there were 5 numbers, multiply it by 4 over 5, you get 8.24, which is what we got right up here. So that works. And you can also do it directly from the standard deviations. Because if you had done this in the calculator, it's only going to give you standard deviation. Let's say you don't need variance. Let's say you need population standard deviation. The calculator, well, I take that back. I'm sorry. The calculator actually gives you both of those numbers. My mistake. It will give you the SA, it'll say SX and then sigma X right there with it. So, all right. But anyway, So if you take 3.209, multiply it by the square root of 4/5, you'll get the 2.87 number. So that's you can convert it from sample to population anytime you need to. I'll put this in the calculator real quick. Now, what is true of the calculator we've talked about does not give you variance. It only gives you standard deviation, but it does give you both standard deviations. 210,659. All right, quit out of that. Go back to stat, calc, 1-bar stats. Yeah, see, there we go. We have, let's see if I can squeeze that in there somewhere. Yeah, let's lift this up a little bit. Let's shrink that a little bit. And we'll be able to look at the two standard deviations. So you see SX is 3.209, which is what the Excel gives, and then the sigma X right below it is what we just calculated for population, 2.87, whatever, 0.5. All right, so, all right, that takes care of that. All right, here's, because that's always a very often asked question, you know, why you divide by n-1 instead of n. If you'd like to read that, feel free to do so. If not, you won't be tested on it. What I usually like to tell people is this, because if you divide by n-1, if you're trying to use a sample to estimate the population, dividing by n-1 will give you a slightly larger number. That way you're sort of on the side of caution, overestimating the value instead of underestimating it. Well, you don't have to worry about that. Now we have, okay, now we're going to look and see how data mean and standard deviation work together in problems. To tell you information about data sets. Mean works better with standard deviation than it does with variance, mainly with units and that sort of thing, but that's okay. So this does, if we have a bell-shaped distribution, which is also going to be called the normal distribution that we'll learn about in chapter 6, but it's the bell-shaped, let's see if they have a picture. Yeah, there's a picture of it. So we say normal, bell shape, same thing. All right. Now, what this called the empirical rule, what it tells you is the following. This says that 68% of your values are within plus or minus 1 standard deviation of the mean. So what that is telling you is that if you took the mean and subtracted the standard deviation and got a number one time, and then added the standard deviation to create an upper value, you've created an interval. So for example, let's say if the the mean was 50 and the standard deviation was 10. If you subtracted 10, that would give you 40. If you added 10, that would give you 60. So then we're saying from 40 to 60, we would expect about 68% of our data to be in there. That doesn't guarantee you're exactly going to get that, but that's roughly what you're expecting. The larger the data sets, the more likely this will hold true. Smaller data sets, even if they are bell-shaped, might not always be true. Okay. So the next interval is plus and minus 2 standard deviations. So if you take the mean, subtract 2 standard deviations, add 2 standard deviations, you're expecting 95% of those values to be in that interval. And the last one is if you take 3 standard deviations below the mean, 3 standard deviations above, create an interval, you're expecting 99.7% of your values to be in that interval. So virtually all of them. You can, we've used this word outlier before. You can probably say that if it's not in that interval, you could consider it an outlier. I think that's a fair assessment. Since you're expecting that close to 100% of your data to be in there. Okay. Oh, there I said it right there. Let's take a look at this example. Okay. So this problem says, suppose we have a data set, mean 60, standard deviation 8, distribution's bell-shaped, meaning also normal distribution. One thing I want to mention is you don't have to worry about whether it's sample mean, sample, or population mean. That's not important. You'll be given a mean and a standard deviation, so you just use what's given. So this is saying if I took 60 minus 8, I get 52. I get 60 plus 1 times 8, because 68% is plus and minus 1. Let's see, 1, 2, 3. I probably won't scroll back up to these, but you can obviously see that it's easy for you to be able to refer back to in the notes. I don't expect you to know these right now, of course, but plus and minus 1, 68%. 2 is 95. 3 is 99.7. So 52 to 68, we would expect about 68%. The next one, suppose we take the mean minus 2 times standard deviation. So it's 60 minus 2 times 8, 60 plus 2 times 8. So we get an interval of 44 to 76. Obviously, that's a wider interval than our first one, so needless to say, you're expecting more numbers to be in there. Therefore, that's where the 95%. So what we're saying about these percentages, that means I'll use this one as an example. I could have said it for the first one, but so this basically says, using this second one we just did, the 44 to 76 right here, that if you went through your data set and you counted how many values were between 44 and 76 and divide it by the total number of values, you would expect about 95% of them to be between 44 and 76 if it's bell-shaped distribution, normal distribution. Yeah, so let's say you had 1,000 numbers, you'd be expecting somewhere around 950 to be in there, since that's 95%. And then the last one is 60 minus 3 times 8, 60 plus 3 times 8. So we're expecting 99.7% of the data to be between 36 and 84. Basically all of them. Okay. So there's a simple little word problem here. It says the mean value from a sample of farms is 2,400, standard deviation of 450. Between what two values do about 95% of the data lie? Assume it's bell-shaped. So 95%, going back to those, 68, 95, and 99.7, Because usually the question I'll get in class, because you've already scrolled past that part of the notes, is but you can go back and look, is the 95% dictates what number is going right there that I've got highlighted. So that means 2. If it was 68%, I would have put a 1 there. If it was a 99.7, I would have put a 3. So the 95% dictates whether it's that it's 2. So the percentage dictates whether it's 1, 2, or 3. So I would take the mean, 2400 minus 2 times standard deviation of 450, and get 1500. I take 2400 plus 2 times 450 equals 3300. And I get an interval of from 1500 to 3300. Now this is a little bit different. Now this is one of 2 ways I put these on test. Either the way we just did or this way, where it's giving you the mean and standard deviation this time, but instead of using the percentage to create the interval, we are given the interval and want to figure out what the percentage is. Now I set this up as an algebraic equation, which is fine, and where k is going to be either the 1, 2, or 3, the number of standard deviations. I could use any letter there. I could use x or whatever. The choice of k is not important. So you can solve it algebraically with one of these 2 equations, and you're going to get 3 as the answer. Or you can do what I just did in the calculator. Here's one way you can do it if you'd like. Is you can either go the low end or the high end. I just chose to subtract. I could have added. I just took 80 and I subtracted standard deviation however many times 12, however many times it took to get to 44. So 80 minus 12 once didn't do it. Minus 12 again, we got to 56. Minus 12 is 34. So it took me 3 times to subtract 12 to get to the number I was looking for, 44. So therefore that meant the number was 3. So that's what we do. So you can do it that way or do it algebraically, but then once you know the answer is 3, that goes back up to the rules for 1, 2, and 3. The rule for 3 is 99.7%. And here's another one. Now I didn't put this one in the calculator, but same thing. You have a mean of 60, standard deviation 13, 47, and 73. If you took 60 minus 13 one time, you'll get to 47, so you'll stop. So 60 minus 13 is 47, so it's only 1 for this one, and 1 translates to 68% by rule. Now, this next example, sometimes I'll do these in class when, live and in person, but this, obviously, you don't need to do any of this for like testing purposes or anything, but I thought it was an interesting example. Is I used Excel to generate some random numbers, and I chose 200. Better the more you do, but I chose it normal distribution. Mean is 60, standard deviation is 8, and I wanted to count to see how close the number of values is to the empirical rule. What if the percentages are close to the empirical rule? So this is just an exercise and just testing a set of data and seeing how it worked. Now I took the data and sorted it. And obviously, Excel would have dumped it down a column, but I just for visual purposes, I took it and made 10 columns of 20. Just obviously, I didn't want to waste a lot of space by going 200 numbers down a column here. So I took them and grouped them in 10 blocks of 20. They're already sorted. So looks like that got a little smashed up there. Let's see. All right, let me fix this. So if I want to count, so we have 200 numbers. So I want to add up how many are in that range of values for each percentage, and then to see how close they are. So smashed here. Let's see. So let me lower this down a little bit here, make some room. Yeah, it didn't. I'll pause. All right, so I clean that up a little bit now. So look, so there's 200 numbers, and you go through. I'm going to skip the part, but you'll count. You'll see there's 136 numbers, and the way I counted this was so between. Just to show you this first one, between 52 and 68. I don't round the numbers. I would be looking for the first number that's slightly above 52. So I would not use this 51.98. I would have used the 52.10659. Then the upper end, I would stop at the closest that I got to 68 and was still below it, which in this case would be 67.98, because the next number is above 68, so I wouldn't use it. So if you count all the numbers between 52.10659 and the 67.98, blah, 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 you'll get 136 numbers, and divide that by 200, and that turns out being exactly 68%. So what I did over here was, on the right, these are the empirical rule numbers, and then in pink are the percentages that I calculated from the data. So those are the empirical values. Okay, so then you can do the next one, 44 and 76. I got 195 out of 200, which is 97.5, and we were expecting 95. And the last one, all of them were between 36 and 84, but obviously 100% is not far off from 99.7%. Okay, so here's what I'm mentioning, you should be close, but no guarantee you're going to match. Chebyshev's theorem. Now for Chebyshev, this is for data that's not bell-shaped. In other words, it is not bell-shaped, not normal, so it can just, a problem can say, not bell-shaped. Or it could say something else, like skewed right, skewed left. Anything that implies that if it's not bell-shaped or not normal, it would fall into this category. Now, not going to spend a lot of time with the empirical rule stuff. That's going to come back when we use the normal distribution, chapter 6. That's very, very important. This we just kind of learn this, and then we won't have to use it for anything else after we use it here. But this says that the data is calculated by this formula, 1 minus 1 over k squared times 100%. K has to be 1, so we won't even have a 1 for this one. And this is very important. See how I've got this red at least all over the place. Pay attention to that, because the wording and the answer for Chebyshev's rule has got to say at least. I mean, it can't say, empirical rule can say about 95% or around 95%. This has to say at least. So watch for that. Any answer it doesn't say at least can't be correct. So with that being said, I generally only use this for 2 and 3 for test purposes. Like I said, this is not a big deal where I think a lot of time needs to be required. So I calculated this, but you don't have to calculate it because it's already done. But since I've done it, since for k equals 2, we're looking for the phrasing at least 75%, with k being the number of standard deviations. And then for 3, 88.9% should be sufficient. So let's look at an example here real quick. All right, mean time for women's track athletes, 400 meters of 57.07 seconds. Standard deviation of 1.05. Shape of the data is unknown. Okay, that's good enough. The fact is it's not bell-shaped or normal distribution. That's enough to imply Chebyshev right there. Find the interval that contains at least 75% of the data. So we go back up here, at least standard deviation, at least 75%. means 2 standard deviations. So that tells us, for this one, that tells us 2 is our magic number for Chevy Chev when it says at least 75%. So we take 57.07 minus 2 times 0.105 and plus 2 times 1.05. And we get an interval of 54.97 to 59.17. All right, so long as you don't confuse this with the empirical rule, you should be good. Here's another one where, all right, here we go, skewed right. Okay, that's enough to tell you right there, it's Chevy Chev. So similar to the empirical rule, we're doing the problem both ways. Now we're trying to find the appropriate percentage. So it's the mean of 60, standard deviation of 3.2, between 50.4 and 69.6. So we need to know how many standard deviations, either adding or subtracting. This time I added. Earlier in my example I subtracted, but it didn't matter. So this time I decided to add and say, okay, how many times do I have to add 3.2 to get to 69.6? And notice it took me 3 times, didn't it? It took me 3 additions of 3.2 to get to 69.6. So the standard deviation value was 3. So going back to the rule up here, 3 is at least 88.9. So once again, the at least is very important. So the answer has to say at least 88.9% of the data lie in the interval of 50.4 and 69.6. And that concludes this lecture.